What if the greatest mystery in the universe is not where aliens are, but why they may never be able to reach us at all? Not because they do not exist, and not because Earth is hidden, but because space itself may be too vast, too hostile, and too unforgiving for any civilization to cross. Tonight, this journey moves through the true scale of the cosmos, the limits of light, the violence of interstellar space, and the quiet laws of physics that may keep every world alone. If this channel brings calm cosmic journeys like this, please like the video, subscribe, and settle in. At the wider scale known to science, Earth does not first sit inside a solar system or a galaxy. It sits inside an expanding universe whose most important feature is not fullness, but separation. The sky appears crowded with stars and galaxies, yet the large pattern is one of immense spacing between island systems of matter. Across that pattern, the basic stage itself changes with time. Space expands. Galaxies that are not tied together by their own gravity do not merely drift through a fixed emptiness. They become farther apart because the fabric between them grows. This is the broadest physical setting for any thought about alien travel, and it already places a severe limit on what can ever arrive anywhere. Modern astronomy reads this expansion in light. A distant galaxy sends out waves of light, and during the long crossing those waves are stretched as space expands. The light shifts toward longer, redder wavelengths. This is called redshift. It does not mean every galaxy is flying away through space like debris from an explosion into pre-existing emptiness. It means the distances between remote systems increase as the universe itself changes scale. The farther a galaxy lies from another on average, the faster that separation grows. This relation is measured across the large-scale cosmos and forms one of the foundations of modern cosmology. This picture matters because travel is always done inside the geometry that exists, not the geometry that might be wished for. On small human scales, distance feels passive. A road remains the same length while a traveller moves along it. On cosmic scales, the road itself can lengthen while the journey is underway. A signal, a probe, or a crewed vessel must cross space that is not static, even before engines, fuel, shielding, or biology become part of the story. The background expansion defines which regions remain in meaningful contact and which regions drift beyond practical reach. The observable universe has a history as well as a size. Light has moved for about 13.8 billion years since the hot early phase of cosmic history, and the oldest light now seen comes from the cosmic microwave background, released when the universe becomes transparent about 380,000 years after the beginning of expansion. That ancient light marks the deepest visible boundary of ordinary observation. It also reminds astronomy that seeing far away means seeing long ago. Distant galaxies are not seen as they are now, but as they were when their light began its journey. Any imagined civilization in a remote galaxy is therefore separated from Earth not only by space, but by time layered into the light itself. Because expansion continues during that travel time, the visible cosmos is larger than a simple multiplication of age by light speed would suggest. The most distant matter now observable lies far beyond 13.8 billion light-years in present-day distance. The universe has had time to expand while the light is en route. This does not create a contradiction. It reveals that cosmic distance and light travel time are related, but not identical. For the question of alien arrival, that distinction is central. A place can be visible in principle and still be separated by such growth of space that direct physical exchange becomes enormously delayed, weakened, or forever prevented. On these scales, there is also a horizon in a physical sense. A horizon is a limit beyond which events cannot affect an observer, not because of poor instruments, but because the structure and evolution of space-time do not permit the influence to arrive. Cosmology contains horizons of this kind. Some regions of the universe are so remote, and the expansion between them and Earth is so persistent, that no signal sent today from there will ever reach here. In the same way, no departure from Earth today can ever reach them. This is not a failure of engineering. It is a property of the expanding cosmos. The idea can sound strange because nothing locally is seen breaking the familiar speed limit set by light. Relativity still stands. No object outruns light through its local region of space. Yet general relativity allows space itself to expand, and at great enough distances the increase in separation can exceed light speed. In that case, a galaxy is not violating physics. Rather, the rule by which distance is measured across space-time evolves in such a way that the gap grows too quickly to be crossed by any light signal sent now. The destination is not simply far, it is receding in the only sense that matters for contact. This alone removes a vast share of possible alien civilizations from any realistic path to Earth. The universe likely contains immense numbers of galaxies, and each galaxy may contain enormous numbers of stars and planets. But abundance does not mean accessibility. Most of cosmic possibility lies outside any reasonable sphere of interaction. If life appears in a remote galaxy on the other side of the observable sky, Earth and that civilization may remain forever outside one another's reachable domain. They may both exist, both build instruments, both wonder about life elsewhere, and still remain physically isolated by the expanding scale of the universe. The expansion itself also changes with cosmic time. Observations show that after the early universe slows its expansion under gravity, the later universe enters a phase of accelerated expansion, commonly attributed to dark energy, a name for the still not fully understood cause of this large-scale effect. This does not mean galaxies near Earth suddenly race away in a dramatic visual sense. It means that on the largest scales, the tendency toward increasing separation strengthens over time. For long journeys, that matters. A voyage planned across immense extragalactic distance does not face a frozen map. It faces a map that stretches against connection. From this widest vantage, the silence around Earth needs no mystery yet. There is no need at this scale to imagine hidden motives, failed courage, or deliberate avoidance. The first answer is geometric and physical. Most of the universe is simply too large and too dynamically separated for travel to bridge it. Civilizations could exist beyond counting, and still almost all would be absent from Earth forever, because the expanding cosmos does not grant all places equal access to one another. Before one reaches galaxies, stars, planets, machines, bodies, or minds, the outermost region has already done much of the work. It has taken the grand field of possibilities and divided it into islands, then carried many of those islands steadily farther apart. The next scale inward is the home galaxy itself, after the widest expansion of the universe is set aside. The Milky Way remains as the first truly local map that still feels almost impossible in size. It is not a small cluster of stars gathered in a neat cloud. It is a vast barred spiral system, broad across, layered in structure, and deep with matter spread over distances that remain far beyond ordinary travel. Inside it, Earth belongs to one star among hundreds of billions. That fact alone changes the meaning of nearness. In everyday thought, sharing one galaxy sounds close. In physical terms, it is not close at all. The Milky Way has a flattened disk where most of its visible stars, gas, and dust are concentrated. That disk contains spiral arms, not rigid arms like the spokes of a wheel, but broad patterns of greater density that move through the galactic material. Near the centre lies a bar-shaped concentration of stars, and deeper still lies the dense central bulge. Around the disk stretches a more diffuse halo containing old stars, sparse gas, and globular clusters, which are compact swarms of ancient stars bound by gravity. At the very centre sits a supermassive black hole, Sagittarius A star, whose mass is measured in millions of suns. All of this forms one gravitational system, rotating slowly over immense spans of time. Its size is difficult to hold in the mind. The visible stellar disk spans roughly 100,000 light-years, and some surrounding structures of gas and dark matter reach much farther. A light-year is the distance light travels in 1 year through empty space. Because light is the fastest known messenger in nature, this unit gives an honest sense of scale. To say that the galaxy is 100,000 light-years across is to say that even light, moving without rest at the cosmic speed limit, takes 100,000 years to cross the main disk from one side to the other. A material craft, moving slower than light as all known matter must, would take longer still. The solar system does not sit near the galactic centre. It lies in the disk, about 26,000 light-years from the centre, in a minor spiral feature called the Orion Arm or Orion Spur, between larger spiral arms. This location is neither central nor extreme. It is an ordinary suburban place by galactic standards, far from the crowded inner regions and far from the thin outer edge. From this position, the night sky seen from Earth reveals the Milky Way as a pale band because human sight looks outward through the flattened disk and catches the combined light of vast numbers of distant stars. That glowing band is beautiful, but its beauty comes from scale so large that it also becomes a measure of isolation. Within the galaxy, gravity holds the whole structure together, but that does not make it compact in any useful travel sense. The Sun orbits the galactic centre at a speed of roughly 220 kilometers per second and takes about 230 million years to complete one orbit. This interval is often called a galactic year. During the entire existence of human civilization, the solar system has moved only a tiny fraction of one such circuit. Continents shift, climates change, species appear and disappear, and the Sun still barely changes its galactic position in any broad way. The galaxy is therefore not only large in distance, it is slow in its total motion, broad enough that even rapid orbital speeds produce changes that remain gentle when measured against its full size. The Milky Way also contains more than what telescopes show directly in starlight. Much of its mass appears to be dark matter, matter inferred from gravitational effects that does not shine or absorb light in ordinary ways. This hidden component forms an extended halo around the galaxy and helps explain how stars orbit as they do. The exact nature of dark matter remains uncertain, but its gravitational role is strongly supported by many kinds of observation. For travel, its presence does not create a visible wall or a direct obstacle in the ordinary sense. What it does reveal is that the galaxy is an even larger and more massive structure than starlight alone suggests. The true gravitational body of the Milky Way extends well beyond the bright ribbon seen in the sky. Gas and dust also shape the galaxy. Cold hydrogen clouds, molecular clouds, and lanes of dust fill parts of the disk. These materials form the raw substance from which stars are born. In denser regions, gravity can slowly pull gas inward until new stars ignite. Elsewhere, old stars age and die, returning matter to the interstellar environment. The galaxy is therefore not static. It is a living structure in the astrophysical sense, continuously cycling matter through stars and clouds over immense spans of time. Yet this activity does not reduce the scale problem. It deepens it. A civilization trying to move across the Milky Way must cross not a simple empty circle, but a broad, structured system whose main feature remains its enormous extent. Even the shape of the galaxy is harder to know from within than it would be from outside. Earth observes the Milky Way from a position embedded in the disk, where dust obscures many lines of sight. Radio astronomy, infrared observations, stellar mapping, and measurements of motion help reconstruct the broader structure. But the map still contains refinements and uncertainties. This is not a weakness of astronomy. It is a reminder of what it means to live inside an object of such size. One does not glance across it. One infers its architecture piece by piece. The same would hold for any civilization elsewhere in the Milky Way. To inhabit a galaxy is to inhabit a system too large to see whole at once. For the question of whether aliens could reach Earth, the Milky Way is the first arena in which the problem becomes concrete. One need not appeal to other galaxies or to the expanding universe anymore. The home galaxy alone supplies a journey space so wide that merely sharing it does little to make arrival plausible. A civilization on one side of the disk and Earth on the other are neighbours only in the loosest cosmic sense. Between them lies a span that light itself needs tens of thousands of years to cross. Any material attempt at passage must confront that same breadth. The galaxy does not forbid motion. It simply stretches the map so far that possibility begins to thin into rarity. Within the great body of the Milky Way, the next inward region is not a cluster of easy neighbours, but the spacing between individual stars. From a distance, the galaxy looks rich with light. Its band across the night sky appears crowded and almost continuous. Yet that appearance comes from looking through enormous depth. The stars do not sit shoulder to shoulder. They are separated by distances so large that even inside one galaxy, the normal condition is isolation. This sparse arrangement defines the local environment around every planetary system and gives interstellar travel its most direct scale. A star is not like a lamp in a city street. A city places many lights within walking distance, often with roads already laid between them. A galaxy does the opposite. It scatters stars through a volume so large that most of the space between them is almost entirely empty. The sun, its planets, and the vast cloud of distant icy bodies that surrounds the solar system together occupy a tiny bubble around one ordinary star. Beyond that bubble lies interstellar space, the thin medium between stars. Then, after a long stretch of darkness, another star system begins. This pattern repeats again and again. The galaxy contains huge numbers of stars, but it does not pack them closely. In the Sun's region of the Milky Way, the nearest star system is Alpha Centauri, a multiple star system about 4.3 light-years away. Proxima Centauri, the faint red dwarf bound to that system, is the closest known star to the Sun. 4.3 light-years may sound modest when compared with the full width of the galaxy, yet its practical meaning is severe. Light, moving at the fastest speed known in nature, still takes more than 4 years to cross that gap. A radio message sent from Earth today and answered at once from a world around Proxima Centauri would still require more than 8 years for the round trip. The nearest known stellar neighbour is therefore already distant enough to turn simple exchange into an event measured in years. This distance becomes more striking when set against the scale of planetary systems. Neptune orbits the Sun at about 30 astronomical units, and 1 astronomical unit is the average distance between Earth and the Sun. Even the distant Oort cloud, whose exact extent remains uncertain, is still thought to reach only a fraction of the way to the nearest star. The space between the outermost known structures of one star system and the inner region of the next remains vast. A star system is therefore not a tile neatly touching another tile. It is a small centre of matter surrounded by a long wilderness. The local stellar neighbourhood contains many stars within a few dozen light years, but even there the spacing remains thin. The typical distance from one star to the next in the Sun's part of the galactic disk is measured in light years, not in planetary units. Some regions are denser, such as stellar clusters and the galactic centre, while others are more diffuse. Yet for ordinary stars like the Sun embedded in the general disk, the common condition is one of separation across dark intervals. This matters because a civilization does not travel from one glowing point to the next by hopping over short gaps. It must commit to crossings that last longer than many human lives unless speeds become extraordinarily high. The night sky can mislead the eye because it collapses depth into a flat dome. 2 bright stars may appear almost adjacent from Earth, while actually lying many light years apart in different directions through the galaxy. Constellations are visual arrangements, not physical neighbourhoods. Orion, Scorpius, Cygnus, and other familiar patterns are shapes created by perspective. If an observer could move far from Earth, the patterns would distort because the stars are scattered through 3-dimensional space at very different distances. This is another reminder that the galaxy is not a painted ceiling. It is a deep volume in which apparent closeness often means nothing physically. The Sun itself is an ordinary star, and that ordinariness is important. It suggests that the spacing around Earth is not exceptional in any obvious way. Many stars in the galaxy are red dwarfs, smaller and dimmer than the Sun. Others are larger, hotter, or older. Some are single stars, while many belong to binary or multiple systems. Planets appear to be common, yet none of this alters the main geometry. Whatever kinds of stars fill the disk, the intervals between them remain large enough that travel from one to another is never a short local excursion in the everyday sense. Even where stars are statistically common, the actual passage between individual systems is long. This sparseness also shapes the chance of accidental contact. If a civilization sends out no deliberate mission and only waits for wandering objects, the galaxy offers little help. Natural bodies do move between stars from time to time. Interstellar objects such as Oumuamua and Comet Borisov show that material can cross stellar space, but such crossings are rare, random, and uncontrolled. They do not create a steady bridge between inhabited worlds. A living or technological civilization cannot rely on chance drift across interstellar distances. The empty space is too broad, and the targets are too small. Even a very fast craft would see the reality of this spacing. Leaving one star does not produce a quick succession of new suns growing large in the window. It produces a prolonged departure from one small region of warmth and light into an immense interval where the destination remains faint for most of the voyage. The traveller would move through years of separation before the next system gradually resolves into a distinct place. Interstellar space is not dramatic because it is full. It is difficult because it is empty on a scale that lengthens every task. The local region around Earth therefore offers no natural shortcut, and no hidden crowding of habitable worlds pressed tightly together. It offers stars spread through darkness, each surrounded by its own small zone of matter, with long distances between them. In this sparse stellar neighborhood, the first practical truth of alien travel becomes plain. Earth does not need to be hidden. It does not need a special defense. It only needs to exist around one ordinary star inside a galaxy where even the nearest neighbors are separated by gulfs that turn motion into a major undertaking. Before speed, fuel, shielding, or survival become decisive. The simple layout of nearby stars already makes arrival difficult. Beyond the spacing between stars lies the next inward layer of the problem, the scattering of places that might actually matter. A galaxy may contain vast numbers of stars, but a traveller does not seek stars in general. It seeks a destination where chemistry, temperature, and long-term stability allow a solid world to remain suitable for life as it is presently understood. This narrows the map immediately. The Milky Way may be rich in suns, yet the set of worlds that resemble Earth, even in broad physical terms, is much smaller, and those worlds are not gathered into convenient clusters. They are spread thinly through a large and mostly unsuitable stellar landscape. Astronomy now knows that planets are common. Observations over the past few decades show that many stars host planetary systems. This changes one old assumption. The galaxy is not a place where the solar system stands alone as a rare arrangement of worlds. Planet formation appears to be a natural outcome of star formation. Dust and gas surround young stars can settle into disks, and within those disks, small grains collide, stick, grow, and eventually form planets, moons, asteroids, and comets. The result is that planets are not unusual objects. They are ordinary products of cosmic history, yet common does not mean equally useful. Many known planets are gas giants, ice giants, or rocky worlds that orbit too close to their stars or too far away for surface conditions like those on Earth. Some worlds may be scorched by intense radiation, some may be frozen over, some may have crushing atmospheres, some may have no substantial atmosphere at all. Some may circle stars that flare violently, bathing their planets in energetic particles and ultraviolet light. Some may move on stretched, eccentric orbits that create extreme swings in temperature. The existence of many planets therefore does not solve the travel problem. It only shows that destinations exist in principle. The harder question is how many of those destinations remain physically favourable over long periods. One useful concept in this search is the habitable zone. This is the range of distances from a star where a planet with suitable atmospheric conditions could allow liquid water on its surface. Liquid water matters because it is one of the clearest chemical requirements for life, as it is known on Earth. The habitable zone is not a guarantee of life. It is only a region where one important condition may be possible. A planet inside that zone can still be dry, toxic, airless, or unstable. Even so, the habitable zone remains a practical filter. It marks where a rocky planet has a chance to be temperate rather than frozen or overheated. That filter still leaves many uncertainties. A star's type matters. Large, hot stars burn through their fuel more quickly and live shorter lives, which may limit the time available for complex life to develop. Small red dwarfs live much longer and are the most common stars in the galaxy, but they often produce strong stellar flares and may expose close-in planets to harsh conditions. A planet's atmosphere matters as well. Too thin, and heat escapes too easily. Too thick, and surface conditions may become extreme. A planet's mass, rotation, internal heat, magnetic field, and geologic activity can all influence whether surface water and stable chemistry endure. Habitability is therefore not a single property, but a balance of many interacting features. This means that even among rocky planets in favourable orbits, truly Earth-like worlds may be uncommon in any strict sense. Earth combines many traits that help maintain long-term surface stability. It has liquid water, a moderate atmosphere, active geology, a magnetic field, and an orbit that remains relatively steady. It circles a long-lived star of moderate type. It also benefits from a large moon that influences tides and helps steady axial tilt over long spans. None of these features alone makes Earth unique by necessity, but together they show that habitability is more demanding than merely being a small planet at the right distance from a star. The search for exoplanets reveals this scattered pattern. Worlds are found around stars in many directions, at many distances, and under many conditions, but no region near Earth appears crowded with obvious twin planets waiting side by side. A potentially temperate rocky world may exist around one nearby star, while the next candidate lies elsewhere, separated by additional light years and additional uncertainty. Some planets are detected only because they pass in front of their stars from Earth's line of sight. Others are found through the slight motion they induce in their stars. These methods are powerful, but they do not instantly provide a full portrait of climate, oceans, continents, or biology. Many targets remain points in a catalogue rather than places understood in detail. This limited knowledge sharpens the difficulty. A civilization planning interstellar travel would not merely choose the nearest star, it would need to choose a star with a reason to visit. That reason most likely depends on the presence of a world with durable conditions for life, science, settlement, or resources. The map of stars is large. The map of promising worlds is smaller. The map of truly known promising worlds is smaller still. The traveller therefore moves within layers of uncertainty. A destination may be distant, and even after all the effort required to reach it, it may prove disappointing or hostile. The same logic applies to any alien civilization trying to reach Earth. Earth may be habitable, but from far away it is not automatically obvious in all its detail. Its atmosphere carries chemical signs that can in principle be studied, and its star is ordinary enough to host rocky planets. Yet Earth remains one target among many possible targets. A civilization elsewhere would face a galaxy full of stars, a smaller subset with planets, a narrower subset with rocky worlds, and a narrower subset still with conditions that appear persistently favourable. Earth might belong in that final group, but it would not stand alone there, and it would not be surrounded by many equally convenient alternatives in one compact region. Suitable worlds are not packed into a nearby chain. They are dispersed through the galactic disk like rare islands. This sparse distribution matters because it removes another silent assumption. It is not enough to imagine that life-bearing planets exist. They must also lie near enough, be identifiable enough, and remain attractive enough to justify crossing the distances between stars. Once the galaxy is filtered through the lens of habitability, abundance gives way to selectiveness. The number of stars stays vast, but the number of truly compelling destinations becomes thinner, more uncertain, and more widely spread. In that quieter map, Earth becomes less a guaranteed meeting place and more one scattered world among other scattered worlds, each separated by long darkness, and each difficult to choose before any journey even begins. After the broad map of the universe, the size of the galaxy, the spacing of stars, and the rarity of suitable worlds are set in place. The next inward barrier is the first hard law that governs every journey. It is not a matter of distance alone, it is a matter of speed. In modern physics, light in empty space travels at a fixed speed, and that speed is not simply very large. It is the upper limit at which information and causal influence can move from one place to another. This limit gives the universe a deep structure. It determines how quickly events can affect other events, how long signals require to cross space, and how matter itself must behave when pushed toward extreme motion. The speed of light is about 300,000 kilometers per second in empty space. This number is so large that ordinary human motion barely registers against it. Earth moves around the Sun at about 30 kilometers per second. The solar system moves through the Milky Way at about 220 kilometers per second. These are remarkable speeds in a familiar sense, yet they remain tiny fractions of light speed. This difference matters because interstellar travel only begins to feel efficient when a craft moves at a significant fraction of light speed, and that is exactly where nature becomes difficult. In classical thought, speed appears simple. A vehicle adds more force, gains more speed, and with enough power might continue rising without any strict upper ceiling. Relativity changes this picture. Einstein's special theory of relativity describes how measurements of space and time depend on motion, and how the speed of light remains the same for all observers moving at constant velocity. From this comes a powerful result. An object that has mass cannot be accelerated up to the speed of light. As its speed rises closer and closer to that limit, the energy required to keep accelerating it rises dramatically. The closer it gets, the harder each additional increase becomes. This does not mean fast travel is impossible. It means there is a boundary built into the behavior of matter and energy. A spacecraft can move at 10% of light speed in principle. It might even move faster in principle if enough energy and engineering were available. But it cannot simply cross the final threshold and become a light-speed vessel while remaining ordinary matter. The law is not a practical recommendation. It is a basic feature of reality as presently understood and supported by experiment. Particles without rest mass, such as photons, move at light speed in empty space. Particles with mass do not. For interstellar travel, this creates an immediate narrowing of possibilities. Consider the nearest star system beyond the Sun, at light speed. The crossing still takes more than 4 years. At half of light speed, it would take more than 8 years, not counting acceleration and slowing. At 1/10 of light speed, it would take more than 40 years. These are idealized figures through empty space, assuming a straight route and extraordinary technology. For stars tens, hundreds, or thousands of light years away, the duration expands in the same proportion. The speed limit does not make travel literally impossible, but it prevents the distances from being compressed into short excursions. No material civilization can simply erase interstellar scale by going fast enough. Light itself also defines what it means to know where something is. Every observation arrives delayed by the travel time of light. Earth is not seen from another star as it is in the same instant. It is seen as it was years ago, decades ago, or longer, depending on distance. The same is true in reverse. Any civilization looking toward Earth from far away sees a past Earth. If that civilization sends a response, the response requires the same sort of time to return. The light-speed boundary therefore shapes not only travel but knowledge. It prevents immediate coordination across interstellar space. It turns every exchange into a delayed interaction with the past. This has a strong effect on the thought that aliens might simply come to Earth if they decide to do so. Decision and arrival are not separated by convenience. They are separated by the same speed limit that governs all physical processes. A civilization 100 light-years away does not merely face a long journey, it also faces old information. It cannot know Earth as Earth is now without waiting a century for light to arrive, and then any action taken in response cannot arrive here for another century at best if it somehow travels near light speed. The structure of cause and effect over stellar distance is therefore slow by necessity. Many familiar science fiction ideas attempt to step around this barrier. Faster-than-light travel, wormholes, and warp drives are common imaginative devices. Some of these concepts have roots in speculative solutions to equations in general relativity, but none exists as an established working method for moving matter, information, or living beings faster than light in the real universe. More importantly, for a physically grounded script, there is no confirmed evidence that any civilization can use such mechanisms, or that the necessary exotic conditions can exist in stable, controllable form. Within accepted physics as it is tested and applied, the light-speed boundary remains firm. This is why the barrier is so central. It is not one engineering problem among many. It is the frame inside which all engineering must occur. A species may improve engines, build larger power systems, design better materials, and automate long voyages, but none of these achievements removes the upper speed limit for matter. Every mission remains trapped beneath it. Every plan must accept that stars are measured in years of light travel, and that any craft must take at least that order of time, usually much more. For Earth, this means safety by distance does not require secrecy. It is enough that Earth orbits one ordinary star in a galaxy where separations are counted in light years and where matter must remain slower than light. Any alien civilization that hopes to arrive must begin by accepting the same law that governs Earth's own astronomy. The destination cannot be reached in an instant, or in a season, or even in one ordinary human span of time unless it lies very near, and the technology is extraordinarily advanced. For all more distant cases, the speed of light turns desire into duration, and motion into patience. It does not merely slow the journey, it defines the boundary beyond which no direct physical shortcut is known. Once the limit of light speed is accepted, distance changes its character and becomes time. A separation between stars is no longer only a measure of space, it becomes a duration that cannot be avoided. In ordinary life, a long route may still feel manageable if a vehicle is fast enough. In interstellar space, that comfort fades. Even very high speeds leave the traveller inside spans of years, decades, centuries, or longer. The barrier is no longer merely how far a destination lies from Earth. It is how long every stage of awareness, departure, crossing, and arrival must take when no object with mass can move at light speed. This can be seen first in the nearest examples. Proxima Centauri lies more than 4 light-years from the Sun. If a craft could travel at 1/10 of light speed, the crossing would take more than 40 years in the frame of the solar system, and that estimate ignores the full time needed to accelerate and later slow down. At 1/100th of light speed, the same journey would require more than 400 years. These are not weak technologies by any familiar standard. They are extraordinarily fast compared with existing human spacecraft. Yet against the distances between stars, even such speeds still create lifetimes of travel. The difference between one star and the next remains measured in human generations, unless velocities become extreme. For more distant targets, duration grows relentlessly. A world 50 light-years away lies close by galactic standards, but not in practical time. At 1/10 of light speed, a one-way mission requires about 500 years before allowing for the additional burden of starting and stopping. At 1% of light speed, it requires about 5,000 years. These are durations longer than recorded human history in one case, and far longer in the other. A civilization may endure for such spans, but a single crew, a single government, a single technical standard, or a single cultural purpose may not. Time, therefore, becomes a filter as severe as distance itself. Signals obey the same general rule. Light is the fastest known messenger, so communication already shows the best case. A message sent from Earth to a planet 10 light-years away takes 10 years to arrive. If an answer is sent immediately, the full exchange takes 20 years, at 50 light-years. The same exchange takes a century, at 100 light-years, 2 centuries. These intervals turn communication into archaeology of the recent past. Every statement received describes conditions that may already have changed long ago at the place that sent it. Every reply is composed in response to an older situation, not a present one. Time delay does not merely slow conversation. It dissolves the possibility of normal dialogue altogether. This delay matters because travel rarely begins in ignorance. A civilization does not cross space without first detecting a target, studying it, and deciding that the journey is worth its cost. Yet all such judgment is made from stale information. Earth seen from a great distance is always an old Earth. A civilization 40 light-years away sees Earth as it was 40 years earlier. If it detects a promising atmosphere, decides to launch a mission, and sends a fast probe, the probe still travels toward a world that may be changed by the time of arrival. For nearby stars, the lag is measured in years or decades. For broader interstellar distances, it becomes much longer. Decision and destination are separated by time thick enough to weaken intention. Duration also changes what a mission is. A short journey can remain under the control of those who begin it. A long journey gradually separates itself from its point of origin. The builders die. Institutions change. Languages shift. Priorities alter. Even if a mission is uncrewed, the society that launched it may not survive in recognizable form until the arrival. The vessel continues, but the original act of choice recedes into history. A one-way crossing of centuries therefore demands not only propulsion, but continuity of purpose. The mission must remain meaningful across spans in which entire civilizations can rise, transform, and disappear. In a biological sense, long travel imposes additional seriousness. Human beings are short-lived compared with interstellar distances, but the same broad truth may apply to many living species elsewhere. A body evolved on a planet tends to belong to ecological and temporal rhythms shaped by that planet. It eats, sleeps, ages, reproduces, and dies on scales much shorter than the crossing between stars. This does not make long missions impossible in principle. It means they must become something other than ordinary voyages. They become projects of suspended life, generation-spanning habitation, machine stewardship, or some other form of existence stretched to match astronomical time. The journey is no longer transportation in the familiar sense. It is an artificial world moving through darkness for longer than a normal life. Time also amplifies uncertainty. A spacecraft on a long interstellar path cannot rely on quick correction from home. A minor navigation error, a technical fault, or a slow degradation in systems may continue for years before its consequences are fully understood. If messages take decades each way, guidance from the origin becomes nearly irrelevant. The vessel must carry almost all the capacity for judgment within itself. This requirement grows with distance. A short mission can be supervised. A long one must become largely autonomous simply because time does not allow close oversight. At the scale of the galaxy, time transforms the meaning of nearness. A star a dozen light-years away is locally close, yet a physical journey to it can still occupy much of a civilization's active memory. A star 100 light-years away may remain permanently inaccessible in any ordinary political or cultural framework, even if physics permits the motion. A place can therefore be reachable in principle and unreachable in practice at the same time. The laws of nature may allow a slow crossing, while the structure of living societies quietly forbids it by demanding more continuity than they can sustain. This is why distance alone does not explain the silence around Earth. Distance becomes silence because time stretches every action until purpose thins out. A civilization may detect Earth and still decide that a journey measured in centuries is not a journey at all, but a transfer of responsibility to distant descendants or machines. It may conclude that no arrival can still count as its own arrival after enough time has passed. In this way, the scale between stars turns motion into inheritance. To reach Earth from even modest interstellar distances is to act across eras, not moments. The crossing remains physically imaginable, but time alters it so deeply that the mission stops resembling a visit and begins resembling a long historical process carried through the dark. After distance becomes time, the journey moves inward again and encounters the next barrier, the cost of motion itself. A craft does not drift to another star by desire or by planning alone. It must be accelerated. Acceleration is the gradual change of speed caused by force acting over time. In space, where there is little friction to slow an object once it is moving. This may sound favourable at first, yet the difficult part is not coasting. The difficult part is giving a large object enough energy to begin the voyage at a meaningful speed, and then, if arrival is meant to be more than a high-speed flyby, giving it enough energy to slow down again. The deeper one looks into interstellar travel, the more the journey is shaped by energy before it is shaped by any other practical concern. Energy in physics is the capacity to do work, and a moving object carries kinetic energy, the energy of motion. The faster an object moves, the more kinetic energy it has. At everyday speeds, this rise is manageable. A bicycle, a car, an aircraft, and even a rocket can be understood as expensive or difficult, while still remaining inside human scales of fuel and power. Interstellar motion changes the scale. A spacecraft heavy enough to carry instruments, structure, shielding, control systems, and perhaps living beings must gain enormous kinetic energy to move at even a small fraction of light speed. The required amount does not feel large only by comparison with present technology. It feels large by comparison with the total energy use of civilizations. This can be seen without using advanced mathematics. If speed is doubled in ordinary motion, the kinetic energy does not merely double. It rises much more quickly. A faster mission therefore asks for disproportionately more energy than a slower one. At the fractions of light speed that make interstellar travel seem remotely practical, the energy grows to severe levels. A probe moving at 1/10 of light speed already carries an immense burden of motion. A larger vessel carrying life support, habitat space, reserves, and protection would require vastly more. The journey becomes, in effect, a struggle to store and direct an extraordinary concentration of energy without destroying the craft that depends on it. Relativity strengthens this burden further. At low speeds, the classical picture of kinetic energy offers a useful approximation. As speed rises toward the speed of light, relativistic effects become important, and the energy required for each further gain increases more sharply. This does not add a new law separate from the speed limit already described. It is the detailed shape of that limit in practice. The universe does not merely say that light speed cannot be reached by matter. It makes the approach toward that limit progressively more expensive in energy. A mission that aims for a very high fraction of light speed therefore does not climb a smooth hill. It climbs a slope that becomes steeper the higher it goes. This means that propulsion is never only a problem of engine design, it is also a problem of power source. A civilization may imagine a perfectly efficient engine, but even perfect efficiency cannot remove the underlying requirement that a certain amount of energy must appear somewhere to change the motion of the craft. That energy must be generated, stored, or delivered from outside. Each option carries its own burden. Stored energy demands fuel or some compact source held on board. Delivered energy demands beams, stations, or other large systems maintained across immense distance. Generated energy demands physical processes powerful enough to feed the mission at the required rate. In every case, the scale becomes daunting. The need to slow down at the far end makes the picture harder. A one-way high-speed flyby is energetically cheaper than a true arrival, because the craft can simply pass the target system without braking. But a civilization hoping to reach Earth in any meaningful sense must not only cross interstellar space, it must also shed most of the kinetic energy it gained at departure. In broad terms, the voyage asks for one vast investment to speed up and another vast effort to slow down. The destination is not reached merely by touching its region. It is reached by matching it closely enough in speed to enter and operate there. In energy terms, stopping is almost as serious as starting. There is also no hidden rescue in the emptiness of space. Empty space does not provide free momentum. A rocket works by expelling mass in one direction so that the craft moves in the other. This is an elegant and proven principle, but it means that motion must be paid for. Momentum is conserved. A spacecraft cannot simply declare a new speed and keep it. It must push against something, either by throwing reaction mass away, by receiving momentum from an outside beam, or by interacting with a field or medium in a physically consistent way. Every realistic method returns to the same core fact. To gain high speed, the craft must exchange large amounts of energy and momentum with the world around it. For living beings, the problem becomes even more severe because high acceleration itself cannot be made arbitrarily strong. An uncrewed probe might tolerate large forces for brief periods if its structure survives. A crewed vessel must preserve bodies, equipment, atmosphere, and internal stability. Long, gentle acceleration is kinder to life, but long acceleration means the engine must keep producing energy over extended spans. Short, violent acceleration reduces travel time during the early phase, yet may exceed what living tissues and delicate systems can safely endure. Energy cost and biological tolerance therefore become linked. The voyage must be not only powerful enough, but also shaped in time so that its own force does not become destructive. All of this leads to a quiet conclusion. The barrier is not that physics forbids motion between stars outright. The barrier is that meaningful interstellar motion demands such large energy that the project begins to resemble planetary industry more than ordinary transportation. A civilization that wishes to send a substantial vessel across light years must gather and control energy on a scale that is difficult even to imagine from the perspective of current human life. The journey stops being a matter of building a ship in the narrow sense. It becomes a matter of commanding resources, infrastructure, and technical discipline vast enough to turn a portion of a world's power into directed motion. For Earth, this means that any alien craft arriving here would represent far more than curiosity and travel skill. It would represent the successful solution to an energy problem of exceptional scale. That alone may make such missions rare. Many worlds may produce life. Some may produce intelligence. Fewer may develop advanced technology. Fewer still may choose to devote extraordinary energy to crossing the dark between stars. The road to Earth narrows again at this point, not because space becomes less real, but because motion itself must be purchased at a cost so high that the decision to travel may fail long before the ship ever leaves home. After the scale of energy is understood, the next inward layer of the journey is the machine that must turn that energy into motion. An engine is not simply a source of power. It is a physical system that converts stored or delivered energy into thrust, the push that changes a craft's speed. In ordinary travel on Earth, engines are common and varied, and their limits are often practical rather than absolute. In interstellar travel, the engine becomes a severe bottleneck because every known class of propulsion carries deep constraints. Some produce too little speed, some demand too much fuel, some remain theoretical in their working form, some might function only as parts of enormous infrastructure rather than as self-contained ships. The result is not that no engine can be imagined, but that no known engine offers an easy path across the stars. The most familiar type is chemical propulsion. A chemical rocket releases energy from reactions between fuels and oxidizers, creating hot gas that is expelled at high speed through a nozzle. The rocket rises because momentum is conserved. This principle is simple, elegant, and fully proven. It has carried human beings to the moon and sent robotic craft across the solar system. Yet chemical propulsion is weak by interstellar standards. The energy stored in chemical bonds is small compared with the energy required for a craft to approach even a modest fraction of light speed. Chemical rockets are well suited for launch from planets, orbital changes, and journeys between nearby worlds, but they do not offer a practical route to another star. Their exhaust speed is too low, so the amount of propellant needed grows beyond reason long before interstellar velocity is reached. Nuclear propulsion appears more promising because nuclear reactions release far more energy than chemical ones. In nuclear fission, heavy atomic nuclei split into lighter nuclei and release energy. In nuclear fusion, light nuclei join and release energy. Both processes are vastly more energetic per unit mass than ordinary combustion. This makes nuclear engines natural candidates for deep space travel. Yet here too the limits are serious. A nuclear thermal rocket, for example, uses a reactor to heat propellant and expel it. It may outperform chemical propulsion, but it still remains far from the performance needed for efficient interstellar missions. It is an improvement, not a transformation. Other nuclear concepts aim higher. A nuclear pulse system imagines a craft pushed forward by repeated detonations behind it, each explosion delivering momentum to a large pusher plate or other coupling structure. On paper, such a system could in principle produce very high speeds. It uses the immense energy density of nuclear devices rather than the gentler output of a steady reactor. Yet this idea brings heavy engineering and political burdens. The craft must survive repeated blasts, manage shock, guide the energy effectively, and carry or manufacture an extraordinary number of explosive units. The system is physically striking, but it turns a spacecraft into a controlled chain of violent events. It also remains untested as a working interstellar machine. Fusion propulsion often appears as the most appealing long-range option, because fusion powers stars and offers high energy release without some of the limitations of chemical fuel. A fusion engine would attempt to harness the joining of the light nuclei and direct part of that energy into thrust. In theory, this could support much higher exhaust speeds and therefore more efficient acceleration over long distances. In practice, controlled fusion is extremely difficult even in stationary reactors on Earth. It requires conditions of temperature, pressure, confinement, and stability that remain challenging after decades of research. To move that difficulty inside a spacecraft and then ask the system to operate reliably for years or decades introduces another level of severity. Fusion is not ruled out by physics, but it is not a solved engine waiting only to be assembled. Antimatter is sometimes discussed because matter and antimatter release enormous energy when they meet. This makes antimatter appear almost ideal in raw energetic terms. However, its practical situation is poor. Antimatter is not mined in useful natural stores. It must be produced through high-energy processes, and present methods yield tiny amounts at extraordinary cost. It must then be stored without touching ordinary matter, which requires elaborate electromagnetic confinement. To build an interstellar engine around antimatter therefore means solving production, storage, control, and safety at scales far beyond any demonstrated capability. Its energy density is astonishing, but its engineering reality remains distant. A different family of concepts tries to move the main power source away from the craft. Beamed propulsion does this by sending energy from afar, often as light or microwave radiation, toward a sail or receiver attached to the spacecraft. In this arrangement, the vessel may avoid carrying so much onboard fuel, which is a major advantage. A very large laser array, for example, could in principle push a very light sail to high speed. This is one of the more physically grounded ways to imagine rapid motion for small probes. Yet the benefits come with strict conditions. The beam must remain tightly focused over enormous distances. The sail must survive intense heating and remain stable. The ground or orbital infrastructure must be vast and precise. Most importantly, such systems work best for very small payloads. Pushing a heavy, protected, versatile spacecraft this way is much harder. Slowing down at the far end is also a major unresolved problem unless another matching beam system already exists there. Ion engines and other electric propulsion systems are highly efficient in one important sense. They can expel propellant very effectively and gradually build speed over long periods. They are already used in space missions where efficiency matters more than high immediate thrust. Their limitation is that thrust is low. They excel in patient maneuvering within the solar system, especially for uncrewed craft, but they do not currently imply practical interstellar travel for substantial vessels. The long acceleration helps, yet the total attainable speed with realistic power systems remains too modest for journeys between stars on useful timescales. Every one of these engines faces the same final judgment. A real interstellar engine must combine high energy, manageable mass, durability, controllable heat, acceptable thrust, long-term reliability, and a method for both speeding up and slowing down. Known concepts tend to succeed in one area by failing in another. Chemical engines are proven but too weak. Fission systems are stronger but still limited. Fusion promises much but remains unsolved in application. Antimatter is powerful but impractical. Beamed systems reduce onboard burden but demand immense external infrastructure and favour tiny craft. Electric propulsion is efficient but slow. The landscape of engines is therefore not empty, yet it offers no mature design that makes alien arrival at Earth an ordinary undertaking. This is why the problem remains so severe. A civilization may understand the stars, master mathematics, and command considerable industry, yet still face the fact that the engines permitted by known physics are either inadequate, immature, or bound to colossal supporting systems. The journey narrows again at the level of the machine itself. It is not enough to have a destination and the will to go. The civilization must also possess an engine that can survive reality, rather than merely look graceful in theory. At present, the known families of propulsion show how hard that demand truly is. Inside the problem of engines lies a quieter and heavier problem, the mass of the ship itself. A voyage between stars is not made by a point of light on a chart. It is made by a real object with structure, tanks, power systems, guidance, thermal control, instruments, and perhaps living passengers. Every piece has mass. Mass is the amount of matter in an object, and the measure of how strongly it resists changes in motion. The more mass a spacecraft carries, the more energy and thrust it needs to accelerate, and the more difficult every stage of the mission becomes. Interstellar travel therefore narrows again at the level of burden. A ship may have a powerful engine, yet still fail as a practical design because the vessel grows too heavy to move efficiently. This burden begins with the frame. A spacecraft must hold itself together under acceleration, vibration, heat, and long exposure to radiation. It must preserve shape and function across years or centuries. That requires beams, walls, joints, tanks, wiring, computers, and redundancy, which is the practice of carrying backup systems so that failure in one part does not destroy the whole mission. Redundancy is important in deep space because help does not arrive. Yet each backup adds mass. Safety improves, but so does weight. The craft becomes more reliable and more difficult to push at the same time. Fuel or reaction mass adds another large burden. A rocket moves by throwing mass backward so that the ship moves forward. This means that the ship must carry not only itself but also the substance it plans to expel. The faster the desired mission, the greater the propellant burden becomes. This leads to a harsh pattern. To carry more fuel, the spacecraft becomes heavier. Because it is heavier, it needs still more fuel to move that extra fuel. Each layer supports the next, and the total can grow rapidly. A mission that appears elegant when imagined as a small vehicle can swell into an immense structure once the mass of propellant is honestly included. This is one reason interstellar craft are often imagined as very light probes rather than as rich, multi-purpose vessels. A small probe can sometimes be accelerated more easily and may require less structure, less fuel, and less internal support. Yet a small probe also carries fewer instruments, less protection, less power reserve, and little room for repair or adaptation. If the goal is only to pass through another system and send back limited data, a small mass may be enough. If the goal is to arrive, study, slow down, and perhaps sustain living beings, the mass climbs quickly. The difference between a probe and a true visiting craft is not merely size, it is a multiplication of difficulty. If living beings are carried, the burden deepens further. A biological mission needs air, water, food, waste processing, temperature control, and protection from contamination. It needs volume, because bodies cannot simply be stacked as cargo and expected to remain healthy. It may need gravity or some substitute for long-term bodily stability, although the full requirements remain under study. It must also carry medical supplies, spare parts, and environmental control systems that keep a small artificial habitat functioning in a place where outside conditions offer no help. Each need adds mass, and each added kilogram must itself be accelerated, protected, powered, and eventually slowed again. Even an uncrewed mission must face the mass of durability. Electronics degrade, moving parts wear, materials become brittle, eroded, or fatigued. A short mission may survive with minimal reserve. A long interstellar crossing cannot. It must carry components that last, or it must carry the means to repair and replace them. Repair systems themselves have mass. So do manufacturing tools, spare materials, and robots if a machine-based maintenance scheme is chosen. The more independent the craft is meant to be, the more it must bring with it. Independence, therefore, costs weight. Shielding is especially important. Space between stars is not completely empty, and radiation remains a long-term danger. To protect delicate systems or living tissue, a craft may need layers of metal, water, specialized materials, or magnetic structures if such systems can be made reliable enough. Physical shielding has a direct cost in mass. A thick shield is safer than a thin one, but it is also harder to move. There is no simple escape from this trade. Interstellar travel asks for a vessel light enough to accelerate and massive enough to survive. Those demands pull against each other from the beginning. Heat management adds another hidden load. Engines, reactors, electronics, and life support systems produce waste heat. In space, heat is not carried away by air. It must be radiated away as thermal radiation. That often requires large radiator surfaces and associated plumbing or structure. These systems add area, complexity, fragility, and mass. A powerful ship therefore becomes not only a heavy ship but also a broad ship in some designs, with large parts devoted simply to shedding excess heat. The ship must carry not just the means to move, but also the means to remain cool enough to function while moving. The mass problem also changes mission planning in a fundamental way. Every object included on board must justify itself. A larger instrument may improve science, but it also demands more structure and more energy. More fuel allows higher speed, but the extra fuel itself becomes cargo that requires yet more fuel. More shielding improves survival, but heavier shielding makes acceleration slower or more expensive. More habitat volume may protect mental and physical health, yet expanded living space adds walls, air, water, and maintenance systems. Interstellar design becomes an exercise in severe compromise. The ship grows heavy because every answer to one danger often creates a new burden somewhere else. For this reason, some of the boldest ideas in interstellar travel try to separate functions. One concept imagines sending only tiny probes. Another imagines automated factories built in stages. Another imagines beings transmitted as information rather than transported as bodies, though no known method can reproduce a full living person this way in practice. These ideas reveal the same truth. The ordinary image of a large, self-contained vessel crossing light years is heavy not only in the literal sense, but in the engineering sense. Mass turns every demand into a compounding cost. By the time the ship is imagined honestly, the journey has changed again. It is no longer just a question of speed and engine power. It is a question of what kind of object can exist at all under the combined burden of fuel, structure, protection, repair, and life support. A civilization may solve one piece and still be defeated by the whole. To reach Earth, an alien craft must not only move across the gulf between stars, it must carry its own world with it, or enough of one to remain useful and alive. That requirement presses downward on every design. In the end, mass becomes more than weight. It becomes the accumulated reality of everything a journey cannot do without. Between the stars, space is not truly empty. After the burden of ship mass is understood, the journey moves inward into the medium through which that ship must pass. This medium is called the interstellar medium. It is the thin mixture of gas, dust, magnetic fields, and energetic particles that fills the galaxy between stellar systems. Most of it is extremely sparse when judged by earthly standards. A laboratory vacuum on Earth can seem emptier than ordinary air by a large margin, yet much of interstellar space is thinner still. This thinness might suggest safety at first glance. It might seem that a ship moving through such a medium would meet almost nothing. The problem is that speed changes the meaning of almost nothing. At sufficiently high velocity, even a very small amount of matter becomes a serious and continuous hazard. The gas in the interstellar medium is made mostly of hydrogen, with helium as the next major component, and smaller amounts of heavier elements. In some regions, the gas is cold and relatively dense, though still extremely sparse compared with any ordinary planetary atmosphere. In other regions, it is warmer, hotter, or more ionized, meaning that atoms have lost electrons and become electrically charged. The density changes from place to place. Some areas are richer in clouds and structure. Other areas are more diffuse. Yet along any long path between stars, a fast-moving spacecraft cannot assume complete emptiness. It must expect to pass through a dilute sea of atoms and ions spread across immense distance. The important point is not how much matter occupies one small patch of space. The important point is how many particles a craft meets when it travels through light years of that medium at tremendous speed. A single hydrogen atom has very little mass. A sparse gas containing only a few atoms per cubic centimetre sounds negligible. But a ship moving at a significant fraction of light speed sweeps through an enormous volume of space over time. It collides with particle after particle, not as one dramatic strike, but as a relentless stream. The voyage converts thinness into exposure. A long crossing through a nearly empty medium can still produce an immense total number of impacts. At low speeds, gas drag in space is minor. A satellite in a very high orbit around Earth feels almost none of it. A probe moving through the outer solar system also treats the surrounding medium as very thin. Interstellar travel at extreme speed is different because collision energy rises sharply with relative velocity. When a hydrogen atom meets the front of a spacecraft moving very fast, the encounter is no longer gentle in effect. The atom may penetrate a surface, ionize material, knock atoms out of place, or generate secondary radiation as energy is deposited into the ship's structure. One atom is small. A steady rain of such encounters over years becomes damage. The front of the craft therefore becomes a special region of danger. The faster the ship moves, the more the medium ahead is concentrated into the direction of travel. In the frame of the ship, particles that were peacefully scattered through space appear to rush inward from the front at enormous speed. This creates a continuous bombardment of the leading surfaces. Those surfaces may heat, erode, charge electrically, or suffer cumulative radiation effects. The rest of the ship remains partly protected behind them, but only if the forward material continues to perform its shielding role. If the front degrades too far, deeper systems become exposed. Hydrogen is the most common gas, and its simplicity does not make it harmless. At ordinary speeds, a hydrogen atom is almost nothing to notice. At relativistic speed, meaning speed where the effects of relativity become important, even the lightest particle can deliver serious energy upon impact. Helium nuclei are heavier and therefore can be even more damaging per collision. In ionized regions of space, charged particles interact not only through direct impact but also through electromagnetic effects. A fast craft may accumulate charge, experience surface sputtering, or require active systems to manage the electrical environment around it. The interstellar medium does not become a wall, but it becomes a constant abrasive presence. This constant presence has consequences for design. A spacecraft meant for high-speed interstellar travel would likely need strong forward shielding. That shielding must be thick enough or clever enough to absorb, deflect, or distribute the energy of incoming particles without failing over time. Yet strong shielding adds mass, and mass makes acceleration harder. The old burden returns inside the new one. A thinner shield is easier to move, but it survives less. A heavier shield survives more, but it demands more energy to reach speed in the first place. The interstellar medium therefore links back to the basic economics of the voyage. Even a dilute gas imposes a tax on design. The difficulty becomes more severe because the medium is not perfectly uniform. A route between stars may pass through regions of somewhat greater gas density, through remnants of old stellar activity, or through changing magnetic environments. Over great distance, variation is normal. A mission planned around average conditions could still encounter harsher stretches along the way. At low velocity, this might matter little. At high velocity, a modest increase in density can sharply raise the total particle flux striking the craft. The ship therefore needs not just a shield for the ideal path, but resilience against a range of conditions that may be poorly known before departure. There is also a navigational problem hidden inside this thin gas. If the craft travels fast enough, the gas ahead can create a kind of radiation and particle environment around the bow of the ship that complicates sensors and surface behavior. Instruments facing forward must work through the very stream of matter that threatens them. Fine external structures become harder to justify. Delicate materials on the leading edge become liabilities. The entire forward architecture may need to be shaped by the simple fact that the road between stars is not empty enough to ignore. For a very slow vessel, these concerns ease. A craft drifting for thousands of years at modest speed would face less severe impact energy from the gas, though it would still face other long-term difficulties. For a fast vessel, however, the interstellar medium becomes one of the main reasons that high speed is dangerous even before dust is considered. The gas between stars is too thin to stop a ship in the ordinary sense, yet too present to leave it untouched. Over enough time and velocity, it acts like a persistent sandblasting of atoms, each tiny on its own, formidable in aggregate. This is why the emptiness between stars offers no free passage. It contains little matter, but little is not none, and speed amplifies every encounter. A civilization trying to reach Earth must therefore design for a voyage through a medium that appears gentle only when distance and velocity are ignored. Once those are restored, the picture changes. The path between stars becomes a corridor filled with invisible impacts, mostly from hydrogen and helium, striking the ship's forward face without pause. In such a corridor, even a successful engine and a manageable mass do not guarantee arrival. The craft must also endure the quiet violence of thin gas met at extreme speed. If the thin gas between stars is already dangerous at high speed, the next inward layer of the journey is more severe. It is not made of atoms spread almost evenly through space. It is made of solid grains, tiny fragments of matter known as interstellar dust. Dust sounds harmless because on Earth the word suggests softness, quiet accumulation, and small weight. In space, that intuition fails. A dust grain drifting between stars may be microscopic, but when a spacecraft meets it at a large fraction of light speed, the encounter carries destructive energy. What seems small at rest becomes violent in motion. In interstellar travel, dust is not dirt along the path. It is invisible shrapnel. Interstellar dust consists of tiny solid particles made from elements such as carbon, silicon, oxygen, magnesium, and iron, often bound into minerals, carbon-rich compounds, or icy coatings depending on the environment. These grains form in the outflows of old stars, in the debris of stellar death, and in the chemical history of the galaxy itself. They mix with the gas of the interstellar medium and help shape the appearance of the Milky Way by absorbing and scattering light. Dark lanes across bright star fields often trace the presence of dust clouds. Astronomy studies them because they reveal where matter gathers and where stars may form. A spacecraft studies them in a different way. It meets them as projectiles. The size of a dust grain varies. Many grains are extremely small, much smaller than the width of a human hair, and some are only a fraction of a micrometer across. Even so, they are large compared with single atoms. This difference matters because solid particles carry more mass in one compact body. When such a grain strikes a fast-moving spacecraft, the collision energy is concentrated into a very small point in a very short moment. The result can be melting, vaporization, cracking, plasma formation, and the ejection of fragments from the surface. A single impact may carve a tiny crater or send a shock through a material. One grain is not a disaster by itself. The problem is the repeated possibility of many such impacts over light years of travel. At ordinary space speeds, dust already matters. Spacecraft in Earth orbit and within the solar system are designed with concern for micrometeoroids, which are small natural particles moving through space. Their impacts can pit surfaces, damage instruments, or puncture exposed materials. Interstellar travel raises the danger sharply because the relative velocity can be vastly greater. The energy of impact rises very quickly with speed. A particle too small to notice in one setting becomes destructive in another simply because motion transforms it. This is why dust becomes one of the most feared features of high-speed travel between stars. It combines small size with large consequence. Unlike gas, dust is not spread as a smooth mist of individual atoms. It comes in grains, irregular in shape and composition, sometimes fragile, sometimes dense. That means the damage it causes can be uneven and sudden. A stream of gas gradually erodes and irradiates. A grain of dust can strike like a minute bullet. If the craft is moving at relativistic speed, even a grain far too small to see can release enough energy on impact to blast material off the ship's forward face. Larger grains, if present, become even more dangerous. Their collisions can exceed what a thin surface can tolerate. A spacecraft, therefore, does not merely need general toughness. It needs a forward defense shaped specifically for concentrated hits. The leading edge of the ship becomes the most exposed region once again. Dust grains are encountered primarily from the direction of motion, because the craft moves into them. In the ship's frame, the path ahead becomes compressed into a narrow cone of incoming danger. This gives designers one slight advantage. The threat is directional. Protection can be concentrated toward the front rather than spread equally over every surface. Yet this advantage is limited. A strong nose shield may help, but it adds mass, and mass returns as a burden on propulsion. If the shield is sacrificial, designed to erode gradually while preserving deeper layers, then it must be thick enough to survive the full mission. If it is too thin, it will not last. If it is too thick, it may make the ship too heavy to accelerate to the speed that created the need for the shield in the first place. Some proposed solutions imagine a layered front structure in which the outermost material absorbs the first impacts and spreads the energy before it reaches the main body of the craft. Others imagine a cloud of particles or a magnetic or electric system placed ahead of the vehicle to intercept incoming matter before it strikes the hull directly. These ideas show that the dust problem is taken seriously in scientific and engineering thought. Yet each remedy introduces new demands. A particle cloud must be maintained and controlled. An electromagnetic method works better for charged particles than for neutral grains, unless the grains can first be altered or broken apart. A physical shield remains the most straightforward idea, but it may need to be massive and heat-resistant. No answer is effortless. The uncertainty of the dust environment deepens the difficulty. Interstellar space is not filled with grains at one uniform size and one uniform density. The distribution changes by region, and the larger grains are the most worrisome because even if they are rarer, they are capable of far greater damage. A mission planner may know the broad properties of the route, yet still not know every dangerous object along it. A tiny grain at extreme speed already matters. A somewhat larger grain could be mission-ending if it strikes a vulnerable point. The ship therefore travels through a medium that is statistically thin but practically unforgiving. Safety cannot depend on the hope that all encounters will remain small. This problem also affects what kind of spacecraft can attempt the crossing. A very small probe with no crew and little surface complexity may accept significant risk. It can be cheap enough, in relative terms, that many copies are sent and a fraction are expected to survive. A large craft carrying a biological community cannot rely on such logic. It must survive nearly every serious encounter. Reliability must be much higher, and therefore protection must be stronger. Dust thus divides mission concepts into classes. What may be acceptable for a disposable probe becomes unacceptable for a vessel whose failure would destroy an entire living expedition. In a quiet way, dust changes the emotional image of interstellar space. The darkness between stars often seems serene, almost empty, and visually still. Yet a ship passing through that darkness at high speed enters a shooting gallery of particles too small to see and too fast to evade. There is no room for ordinary reaction time. Detection may come only at the instant of impact or not at all. The defense must already be present, built into the material and form of the craft. The success of the mission depends on preparation, not quick response. For Earth, this means that an alien civilization trying to cross the gulf between stars must do more than solve energy and time. It must also survive a path where minute solids become weapons through motion alone. The dust between stars does not need to be abundant to be dangerous. It needs only to be there, and it is there, across enough distance and enough velocity. Those scattered grains become one more reason why arrival at Earth is not simply a matter of building a faster ship. The road itself is seeded with impact waiting to happen, and each tiny grain carries the power of speed concentrated into a point. In that sense, interstellar dust is small only before the journey begins. Beyond gas and dust lies a danger that does not need solid impact to cause harm. It moves through empty space as high-energy particles and radiation, often silent, invisible, and cumulative in its effects. This is the next inward layer of the journey. Even if a spacecraft could survive the burden of mass, the cost of propulsion, the thin gas between stars and the strikes of dust, it would still have to endure a long passage through a radiative environment that slowly injures living tissue, disturbs chemistry, and degrades machines. Interstellar space does not burn like a fire and does not crash like a storm, yet it exposes a vessel to a steady background of energetic damage that becomes serious over long durations. One part of this environment is cosmic rays. Cosmic rays are high-energy particles, mostly atomic nuclei and some electrons, that move through space at very high speeds. Many are protons, which are the nuclei of hydrogen atoms. Others are heavier nuclei from elements such as helium, carbon, oxygen, or iron. They are launched by violent astrophysical processes, including supernova explosions and other energetic events in the galaxy. Their exact origins across the full energy range remain an active area of study, but their presence is well established. They cross interstellar space for long periods and can penetrate matter when they strike it. A cosmic ray does not need to be large to be harmful. Its danger comes from energy. When such a particle passes through tissue or material, it can ionize atoms along its path. Ionization means removing electrons from atoms or molecules, which disrupts chemical bonds and changes the local structure of matter. In electronics, this can alter signals, flip stored bits, or damage components. In living cells, it can injure proteins, membranes, and especially deoxyribonucleic acid, the molecule that carries genetic information. Some damage can be repaired by living systems, some cannot. Over time, repeated exposure raises the chance of mutation, cancer, sterility, tissue injury, or broader system failure. This makes radiation different from dust in one important way. Dust threatens the hull through sudden impacts. Radiation threatens both hull and interior through penetration and accumulation. A craft may appear intact from outside while its electronics slowly degrade and its occupants absorb dose over months, years, or centuries. The dose is the amount of radiation energy deposited in matter, and when dose accumulates beyond tolerable levels, consequences follow. A short mission may absorb little enough to manage. A long interstellar voyage magnifies the total burden simply because the exposure continues without relief. Interstellar space is not uniformly hostile in the same way everywhere, yet it lacks the strong natural protections that planets can provide. Earth has an atmosphere and a magnetic field. The atmosphere absorbs much harmful radiation and breaks up many incoming energetic particles. The magnetic field deflects a portion of the charged particle environment and helps shape protective regions around the planet. Even within the solar system, the Sun creates a broad bubble called the heliosphere, formed by the solar wind and magnetic field carried outward through space. This bubble does not remove all cosmic rays, but it influences the local particle environment. A spacecraft leaving its home star's protective domain and entering deep interstellar space may lose much of that shelter. Stellar radiation adds another element. A star emits light across many wavelengths, including visible light, infrared radiation, ultraviolet radiation, and in some cases stronger high-energy outputs such as X-rays. Near a star, this radiation field can be intense and variable. Far from stars, the steady glow weakens with distance. Yet radiation from the departure system and arrival system still matters during those phases of the journey. In addition, energetic particles from stellar flares and stellar winds can create periods of increased danger around active stars. A civilization trying to reach Earth from another system must therefore think not only about the quiet middle of interstellar space, but also about the hazardous passages near stars where radiation conditions may become much harsher. High-energy particles also create secondary radiation when they strike shielding or the hull. This is one of the cruel complications of the problem. A wall that stops part of the incoming radiation may itself become the site of new particle showers and fragments produced by the impact. In other words, shielding is necessary but not simple. Dense materials can block some threats effectively, yet the interactions inside those materials may generate additional radiation that penetrates deeper into the craft. Lighter materials rich in hydrogen, such as water or certain polymers, can sometimes be useful because they reduce some forms of secondary particle production. But such materials take up space and mass returns once again as a central burden. For electronics, radiation damage may be immediate or gradual. A single energetic particle can produce a transient error, changing the state of a memory cell or disrupting a processor. This is often called a single event upset in engineering language, though the underlying concept is plain enough. One particle passes through a critical part of the circuit, and the system briefly misbehaves. Over longer periods, repeated exposure can degrade semiconductors, weaken sensors, embrittle materials, and reduce the reliability of power systems. A long mission therefore cannot rely on delicate components alone. It needs hardened systems, error correction, redundancy, and repair capacity. Each protective step adds complexity, and often mass as well. For living beings, the issue is more severe because cells are not simple components that can always be replaced. Biological tissues have varying sensitivity to radiation. Bone marrow, reproductive organs, the digestive system, and the nervous system may all suffer in different ways under prolonged exposure. Even when acute sickness does not appear, long-term risk grows. This does not mean life cannot travel through space. It means the voyage requires a degree of protection difficult to provide across long durations. A brief mission beyond a planet's protective envelope is one thing. A crossing between stars is another. Time turns manageable exposure into cumulative threat. One possible response is thick shielding, water, fuel, food stores, and structural materials might be arranged around living quarters to absorb part of the radiation field. Another response is to send machines instead of biological travelers. Machines can be damaged too, but they do not suffer cancer or fatigue in the biological sense. Even so, machines still need hardened electronics and durable materials, and very long missions challenge them as well. There is no perfect escape here. Radiation asks every design the same question: can the craft remain functional and, if alive, remain alive after years upon years of invisible injury? This is why empty space is not empty in any useful protective sense. A ship may float in darkness with no atmosphere outside and no visible threat nearby. Yet energetic particles continue to cross its path and enter its structure. The harm is not cinematic. It is statistical, chemical, and cumulative. Over enough time, that is fully sufficient. To reach Earth, an alien craft must therefore survive not only visible obstacles, but also a long immersion in radiation that slowly works inward through matter, system by system and cell by cell. In that radiative silence, the voyage becomes a contest not against one blow, but against accumulation itself. after the long exposure to radiation is understood, the journey moves inward again to a feature of high-speed travel that often creates confusion. This feature is time dilation. Time dilation is the slowing of elapsed time for an object moving at very high speed relative to another observer. It is not an illusion in the careless sense, and it is not a trick of poor measurement. It is part of the structure of special relativity. Clocks in different states of motion do not simply carry one universal pace with them. They can record different amounts of elapsed time between the same broad departure and arrival events. For interstellar travel, this means that a fast traveler may experience less time than the people who remain behind. This sounds at first like a kind of escape from distance, but the escape is only partial. Time dilation changes the traveler's experience of the journey. It does not remove the large-scale barriers that separate the stars. A clock is any system that marks regular intervals. It may be mechanical, electronic, atomic, or biological. In relativity, clocks are not privileged by their design. Any stable process that measures duration can serve. If one clock remains on Earth and another travels at very high speed through space before returning, or before being compared again in principle, the moving clock can record less elapsed time than the Earth clock. This result is not speculation. It has been confirmed in experiments with precise clocks carried on aircraft, with fast-moving particles created in laboratories, and with many technologies that rely on relativistic corrections. Time dilation therefore belongs to tested physics, not to imaginative storytelling. The effect is small at ordinary speeds. A ship moving like present-day human spacecraft experiences such a tiny difference that it hardly matters. As speed rises toward a significant fraction of light speed, the effect becomes more noticeable. At 1/10 of light speed, the difference is modest. At half of light speed, it is larger. At 9/10 of light speed, it becomes strong. At still greater fractions, the traveller's own elapsed time can become much shorter than the time measured by observers in the departure system. A voyage that seems to last many years from Earth may feel somewhat shorter, or much shorter, on board the ship, depending on the speed profile. This creates one of the few genuine consolations in relativistic travel. A biological crew travelling fast enough may not need to live through the full Earth frame duration of the crossing. The shipboard time can be reduced. If a journey to a distant star takes decades or centuries as measured from Earth, the crew might experience less. In that narrow sense, relativity softens the human burden of long travel. The crew ages according to the time recorded on board, not according to the time recorded by distant observers. Muscles weaken, cells divide, and memories accumulate according to shipboard time. The travellers do not personally endure every year that passes elsewhere. Yet this softening has strict limits, and those limits are essential to the present topic. Time dilation does not permit a material craft to outrun light. It does not let information reach Earth before light from the same departure could do so. It does not change the fact that, in the frame of Earth and the target system, a real interval still passes between launch and arrival. The ship may experience a shortened journey, but Earth still waits through the longer one. This is the central distinction. Time dilation changes whose clock records which duration. It does not erase the causal structure set by the speed of light. This matters greatly for the claim that aliens could simply reach Earth if relativity helps them. Relativity helps only in the sense that the travellers may age less. It does not help Earth receive them sooner than the physical travel time permitted by their velocity. Suppose a civilization launches a ship from a system many light years away. If the ship moves at very high speed, the crew may feel that the crossing takes fewer years than an outside observer would calculate. But Earth does not meet them according to their private experience alone. Earth meets them only when the ship actually arrives here, and that arrival still occurs after the appropriate external duration. For Earth, the journey remains long. For the travellers, it may feel shorter. Both statements are true at the same time. Time dilation also does not solve the problem of stale information. A civilization far away sees Earth as it was in the past, because light from Earth requires time to reach them. If it launches a mission based on that old picture, the mission still heads toward a world that may have changed long before arrival. The crew may experience a compressed voyage, but the age of the information at launch remains what it is, and the elapsed time in Earth's frame during the crossing remains what it is. Relativity cannot make an old observation become current. It cannot create immediate knowledge across interstellar distance. Another common confusion concerns communication during the journey. A fast-moving crew may feel that their own clocks run in a way that shortens their voyage, but any messages they exchange with home or with Earth still obey light speed limits. Signals remain delayed. If the ship sends a message while far from Earth, that message does not leap ahead because the crew experiences less time. It still crosses space at light speed and arrives after the corresponding interval in the frame relevant to the receiving system. Time dilation therefore does not restore normal conversation across the stars. The communication problem remains. There is also no free benefit in energy. A ship does not gain time dilation without first being accelerated to very high speed, and that acceleration demands the same severe energy already described. In practical terms, the stronger the time dilation benefit one hopes to enjoy, the closer the craft must move to light speed, and the more punishing the energy demand becomes. Time dilation is therefore not an alternative to the propulsion problem. It is a consequence of entering its most difficult regime. The travellers gain reduced personal elapsed time only by paying with extraordinary velocity, extraordinary energy, and all the accompanying risks from gas, dust, and radiation. For the travellers themselves, the effect can also carry a quiet cost. A crew may leave home and experience only a limited span on board, yet arrive to find that much more time has passed in the wider galaxy. Even if a mission succeeds physically, it may still sever the travellers from the society that launched them. Friends, institutions, languages, and cultures may all age far beyond the shipboard experience. In this sense, time dilation does not simply shorten travel. It separates the traveller's life from the history outside the ship, so the role of relativity remains precise and narrow. It changes the experience of duration on board a fast craft. It confirms that different observers can record different elapsed times without contradiction. It offers some relief to those who travel at immense speed, but it does not make Earth easy to reach. It does not reduce the energy cost of becoming relativistic. It does not remove the light speed barrier. It does not update old information instantly. It does not let arrival occur sooner in Earth's frame than physics allows. For any alien civilization trying to come here, time dilation is therefore not a hidden doorway through the laws of nature. It is only the strange but lawful way those laws treat time once the voyage becomes extreme enough to be truly interstellar. After the physics of speed, energy, matter, and time are placed in order, the journey moves inward once more and reaches the question of continuity. A spacecraft does not cross interstellar distance through engineering alone. It also depends on the lasting stability of the civilization that conceives it, builds it, launches it, and in some sense remains responsible for it. This introduces a barrier different from gas, dust, or radiation, yet no less serious. A voyage between stars may require spans of time so long that the problem is no longer only whether a machine can survive. It becomes whether a culture, an institution, a body of knowledge, or a chain of purpose can survive long enough to carry the mission through to completion. On Earth, civilizations change quickly when measured against astronomical time. Languages shift, political systems rise and fall, religions expand and divide, economies transform, scientific frameworks improve or are replaced. Even where continuity seems strong, the details of life, law, and meaning can alter greatly over centuries. Recorded human history covers only a few thousand years, and within that short interval, compared with the age of the galaxy, there have already been repeated episodes of collapse, migration, conflict, and reinvention. Technology often advances, but it does not do so as a straight and permanent ascent. It depends on social stability, energy supply, education, material resources, and institutional memory. Remove enough of these, and sophisticated capabilities can weaken or disappear. This matters because interstellar travel on realistic timescales may outlast the initiating form of the society that begins it. A mission to a nearby star at modest but extraordinary speed may require decades. A mission to a more distant but still local target may require centuries. A slower mission may require longer still. Over such intervals, the originating civilization may remain wealthy, or it may fragment. It may continue to honor the mission, or it may decide that the mission no longer matters. It may even forget the detailed reasons for launch if the chain of transmission fails. The spacecraft can be built at one moment in history, yet its success depends on historical stability extending far beyond that moment. Knowledge itself requires maintenance. A technical society does not store its abilities only in machines. It stores them in people, institutions, education systems, archives, manufacturing networks, and habits of verification. A spacecraft moving between stars may need software updates, interpretive judgment, replacement plans, or continued monitoring from home, even if much autonomy is built into it. If the civilization that launched it changes too deeply, the mission may become an artifact without a living framework to understand or sustain it. The hardware may survive, but the surrounding meaning and competence may erode. A long voyage, therefore, depends not only on durable material but also on durable knowledge. Purpose is equally fragile. A mission begun under one cultural mood may seem noble, urgent, or inevitable. After enough generations, that same mission may appear expensive, irrelevant, or ethically doubtful. New priorities may emerge. A planet under environmental strain may turn inward. A civilization facing internal conflict may divert resources. A culture transformed by new philosophies may reject expansion altogether. None of this requires disaster. Ordinary historical change is enough. The trouble is that interstellar travel stretches a single act of will across periods long enough for will itself to evolve beyond recognition. If the mission is uncrewed, autonomy can reduce some of these demands. A probe directed by machines does not need daily human encouragement. It can execute plans on its own if its systems remain functional. Yet even autonomous missions are not free from the continuity problem. They must be designed with extraordinary foresight because later correction may be impossible or irrelevant across long communication delays. Their goals must be narrow enough to survive centuries without revision, or flexible enough to adapt intelligently without drifting away from the mission's original meaning. This requires a form of foresight difficult even for short projects, and much harder for those aimed across eras. If the mission is crude, continuity becomes more intimate. A large interstellar vessel carrying living beings over generations is not merely a craft. It is a small society. Such a society must preserve health, order, technical skill, reproduction, conflict resolution, and a shared understanding of why the voyage continues. Children born on board would inherit the mission rather than choose it in the same original sense. Over time, their relationship to the destination could change. The ship would need not only engines and shielding, but also culture, law, memory, and education robust enough to endure isolation. The voyage would become a social experiment on a scale never tested. Its failure could come from internal drift as easily as from external damage. Even a shorter crewed mission faces related issues. Psychological endurance matters, isolation from a home world, delayed communication, confinement, and the absence of natural environments may alter behavior and judgment over long spans. Machines can be redundant. Human communities require something more subtle. They require trust, legitimacy, and a stable narrative that justifies hardship. These are not minor details added after the engineering is complete. They are part of the engineering in the broader sense. Because a mission involving intelligent agents fails if its inner life collapses before its outer systems do. There is also a deeper uncertainty that cannot be measured directly. Humanity has only one confirmed example of a technological civilization, and it is young. Science can estimate orbital mechanics, radiation dose, and material stress with increasing precision. It cannot yet state with equal confidence how long a complex technological civilization normally remains coherent, expansionist, resource-rich, or internally stable. For alien societies, this uncertainty is even greater because there are no confirmed cases to compare. Observations indicate that stars and planets are common. It remains uncertain how often civilizations endure for the spans that interstellar travel may require. This uncertainty does not prove that long-lived civilizations are rare, but it prevents easy confidence that they are common. For that reason, the silence around Earth may contain a temporal filter as much as a spatial one. A civilization may arise, gain science, build instruments, and still occupy only a brief window in which it has both the ability and the desire to launch a mission across the stars. Before that window, it is not yet capable. After that window, it may turn to different aims, lose stability, or disappear. If the window is shorter than the travel time to Earth, then the mission never begins, or begins only rarely. In that case, the barrier is not a single law of physics, but the combined difficulty of keeping intelligence, industry, and intention aligned over immense time. This is why interstellar arrival may fail long before the destination system is reached. The vessel must survive, but so must the chain of meaning behind it. A civilization that cannot preserve knowledge, purpose, and technical order across centuries may never complete the kind of undertaking that reaching Earth requires. The stars separate worlds by distance, but time then presses upon societies and asks whether they remain themselves long enough to answer that distance with action. Many may not. In that quiet possibility, the road to Earth narrows again, not in the emptiness between stars, but in the historical life of the travellers themselves. At the final inward layer of the journey, the problem changes once more. After the great scale of the universe, the breadth of the galaxy, the spacing of stars, the thin distribution of habitable worlds, the barrier of light speed, the long burden of time, the cost of energy, the limits of engines, the weight of the ship, the gas between stars, The danger of dust, the pressure of radiation, the strange effect of time dilation, and the difficulty of civilizational continuity. The traveller still does not simply arrive. It reaches the threshold of one star system and faces the last challenge of all. Earth is not a large, still target hanging alone in space. It is a small moving world in orbit around an ordinary star, buried among other bodies, wrapped in light, and protected by the simple fact that successful arrival requires precise slowing as much as successful crossing requires speed. The solar system is broad on a human scale and small on a galactic one. That combination makes it deceptive. From interstellar distance, the Sun is only one star among many. It shines more brightly than Earth by an enormous margin, and any approaching craft first encounters the system as a luminous central object surrounded by faint companions. The planets do not advertise themselves equally. Large planets may be easier to detect through their gravitational influence or reflected light. Small rocky planets are harder. Earth is especially modest beside the brightness of the Sun. To find it from afar is not impossible in principle, but it requires knowledge, measurement, and patience. One must know not only that the solar system exists, but which small orbiting world is the true target. This is not a trivial distinction. A planet does not remain fixed in one place. Earth moves around the Sun at high speed, completing one orbit in 1 year. It rotates, reflects changing light, passes through seasons, and shares its system with other planets, moons, comets, dust, and the broad gravitational influence of the Sun itself. An arriving craft cannot aim at a single frozen point and expect success. It must predict where Earth will be when the craft reaches the inner system. Any error in earlier navigation can widen over interstellar distance into a large miss at the end. The closer the craft comes, the more precise the corrections must become. The Sun also changes the character of the problem because arrival is not merely a matter of entering its neighbourhood. A craft approaching from interstellar space carries its own velocity relative to the solar system. If that velocity remains high, the craft does not gently join the system, it plunges through it. A fast interstellar ship that fails to slow down enough may flash past the planets in a brief passage and vanish back into interstellar space. In that case, the crossing between stars is achieved, but Earth is not truly reached. The difference between passage and arrival depends on braking, the process of shedding speed until the craft can be captured by the Sun's gravity, or guided into a controlled path through the planetary region. Braking is difficult because the same energy invested in acceleration must in some form be removed. A ship approaching Earth after years of interstellar travel still carries enormous kinetic energy if its speed remains high. To slow it requires engines, sails, magnetic interaction, gravitational maneuvers, or other methods strong enough to change its motion without destroying it. A gravity assist, which uses the motion and gravity of a planet to change a spacecraft's speed and direction, is useful in the solar system for human probes, but it cannot by itself solve every arrival problem for a fast interstellar craft. If the incoming speed is too great, the available natural assists may be insufficient. The ship must therefore arrive with a braking strategy already built into the mission. This is especially serious for a civilization trying not merely to observe Earth, but to enter near it. A flyby can collect some information. A true arrival requires more. It requires orbital insertion, descent, station keeping, or at the very least prolonged controlled presence within the system. Each of these demands that the relative speed be reduced to manageable levels. The ship must move not only toward Earth, but with Earth closely enough that the planet does not race away beneath it. This final matching of motion is the quiet technical act that turns a distant crossing into an actual meeting. The environment of the solar system introduces further complications. The sun emits light, heat, and charged particles in the solar wind. Its gravity shapes every path within the system. The planets perturb one another. Dust, small bodies, and debris remain present in low densities. A craft coming from deep space must transition from the comparatively simple geometry of interstellar cruise to the richer gravitational and radiative structure of a star system. Navigation grows more demanding, not less. As the destination nears, the target is smaller, the required precision greater, and the acceptable range of error narrower. Earth itself is also protected by its own local conditions. It has an atmosphere. An atmosphere is useful for life, but it is dangerous for arrival at high speed. A spacecraft entering too fast faces extreme heating from compression of air ahead of it and frictional interaction with the atmosphere around it. Human re-entry from Earth orbit already requires careful thermal protection. Return from the Moon requires more. Arrival from interstellar travel would be a categorically different problem unless the craft first reduces its speed enormously before any atmospheric encounter. No intelligent civilization reaches Earth by simply diving in from the dark between stars. It must spend large effort becoming slow enough for Earth's air and gravity to become survivable rather than destructive. Even locating Earth as a living world may remain harder than often imagined. From a great distance, Earth is one pale, rocky planet close to a bright star. Its atmosphere may reveal chemical imbalance associated with life, and its radio emissions, if detected during the relevant era, may add another clue. Yet such signs are subtle against distance, time delay, and stellar glare. An alien civilization does not approach a glowing sign marked Earth. It approaches a system of moving bodies and must identify one small world among them with enough confidence that the final approach is worth the risk and cost. This means that the end of the journey demands the same qualities as the beginning, but in a tighter form. It demands knowledge, precision, energy, durability, and time. A craft that survives interstellar space but cannot break remains a visitor only in the narrowest sense. A craft that enters the solar system but misjudges Earth's position wastes the whole crossing. A craft that finds Earth but cannot adapt to its atmosphere, gravity, and orbital motion still fails to arrive in any meaningful way. The final threshold is therefore not ceremonial. It is physically exacting. In this last region, Earth becomes safest not because it hides, but because it is small, moving, and difficult to match. The sun's light conceals it from simple sight. The solar system's structure demands correct timing. The need to slow down turns success into a second great energy problem after the first. The atmosphere punishes reckless entry. By the time an alien civilization reaches this threshold, it has already solved almost every earlier challenge. Yet one challenge remains, calm and absolute. Earth must not only be found, it must be met at the right place, at the right time, and at the right speed. Without all three, the long voyage ends not with arrival, but with passage through a system that never truly receives the traveller at all. The thought of alien arrival often begins with wonder and ends with fear, yet the physical picture remains quieter than either feeling. Earth circles an ordinary star in a galaxy of great breadth. Inside a universe whose larger structure widens with time, between one inhabited world and another, if others exist, lie long distances that do not soften merely because intelligence appears. The laws that govern light, motion, energy, matter, and time remain in place for every civilization alike. They do not bend for curiosity. They do not shorten the dark between stars out of urgency or ambition. In that calm framework, Earth does not need to be unreachable in the absolute sense. It only needs to be difficult enough. A world may be known and still remain unvisited. A signal may be seen and still remain unanswered. A destination may be real and still sit beyond the practical horizon of engines, shielding, patience, and historical continuity. The silence of the sky can therefore arise without drama. It can emerge from distance, delay, expense, and fragility, all working together with no single barrier needing to be perfect on its own. This leaves the night in a gentler form. The stars continue to shine across immense separation. Planets continue their small paths around them. Light continues to travel faithfully, carrying old news across deep time. If life exists elsewhere, it likely lives under the same measured rules, looking outward through its own sky, facing its own long intervals, and meeting the same patient resistance from the structure of the cosmos. Earth remains where it has always been, a small moving world beneath a thin atmosphere, held close by gravity and held apart by distance. The darkness beyond it is not empty of possibility. It is simply vast, lawful, and slow, and that slowness may be enough to keep worlds to themselves for ages beyond measure.